A briefer summary of the preceding. We have power function here, power function here. And I'm not sure I really did a good job of actually constructing graphs of actual power functions. I just slopped these graphs down. But assuming they are, this will illustrate my point. We have a lesser y factor here than we have here. And if you've done several of these, you'll understand clearly that this does have the lesser y factor than this. Now we look at slopes at 3 points on each graph and how the slopes develop. Okay, so we do a tangent line here, tangent line here, tangent line here. Here's the x value for the point of tangency here, the x coordinate of the point of tangency here, x coordinate of this point of tangency. We have slopes. Now I draw little triangles indicating that we can use to indicate the slope. I've used approximately the same run on each triangle so that the relative values of the rise give us relative values of the slope. And I estimated that the rise here is about maybe 1.5 times the rise here, which is about twice the rise here. So that the barbarians are at the gate, apparently. Okay. Yeah, halls need to be buffed. It's a weekend, no complaint. So when we do this, in this case, we get a graph showing the slope of the tangent line versus the x-coordinate of the tangent line that's concave down. And here, using the same ideas, we get a graph that's concave up. These slopes increase much more quickly relative to one another than these slopes. Our numerical example made that plausible. Hopefully you understand the idea here, and whether I've done all this really accurately or not, you get the idea. So that as we increase the y factor, our slope graphs change shape. We go from this shape to this shape. So here we have this shape, here we have this shape, and what happens at the intermediate values of the y factor? Well, we have a significant downward concavity here. Here we have only a little bit of downward concavity. Ignore this for a minute because we want to make this plausible. Here we have a little bit of upward concavity. Now here we have even more upward concavity. And this is the progression we would expect if we progressively increase the y factor. So, between a little bit of downward concavity and a little bit of upward concavity, we expect maybe that there would be a sweet spot where we have no concavity, no downward concavity and no upward concavity. And that would give us, what, a straight line graph through the origin. So, the question is there a sweet spot? Is there a y factor that results in a graph where the slope versus point of tangency versus the x-coordinate of tangency graph is a straight line? If so, then what y factor is it that gives us the sweet spot? We can investigate this in many ways. The sweet spot where the concavity is neither up or down, that would be a straight line graph of the slope versus the x value of the point of tangency. And a related question, these y factors were all bigger than 1. What if the y factors between 0 and 1? Okay, what do the graphs look like, and how do the slope graphs behave for those y factors?